In the US alone, 2.8 million people suffer from antibiotic-resistant infections, and as a result, 35,000 people die each year from these causes. Antibiotic resistance is when bacteria develops resistance against our antibiotics, and as a result, this becomes a huge problem considering how in past decades, overprescription of antibiotics and overuse can lead to the development of far more deadly and infectious bacteria that we won't have any treatments against. However, synthetic circuits provide a potential solution. Synthetic circuits are created by using biological parts such as DNA and RNA and using them to perform digital functions, which are similar to ones that we find in electrical circuits. So when we think of our computer hardware, they're made up of electrical circuits, and what controls the electrical signals are transistors. And within these transistors, there are components called logic gates, which allow for more complex functions to occur. So for the sake of the presentation, we're only going to be going over the most basic logic gate, which is called a NOT gate. And for logic gates in general, the concept is that based on the rules of the function, it will take in an input and produce an output. So for our inputs, we only have either a 0 or 1, where 0 is off and 1 is on. And so for a NOT gate, if we have an input of 0, it will create an output of 1 and vice versa. And so for my project, I developed a bistable switch using E. coli, and based off of my circuit, the presence of specific biomolecules could lead to the self-destruction of E. coli. So for a bistable switch, you can think of it as your iPhone settings, where if I want to turn my Bluetooth on, for example, I just have to click the button and it will glow a bright blue. In the same way, if I wanted to turn off my Bluetooth, I just have to click the button again. And that just shows how we only have two potential options, where either our Bluetooth is on or our Bluetooth is off. There's nothing that happens in between. It's not like our brightness levels or our volume levels, where we can kind of swipe through and come up with different outcomes. So these are just screenshots from my actual project, or on the left, it just shows an overview of the actual circuit. But if you click in, you can kind of see the parts that make up each specific component. So this graphic kind of illustrates how it would work and how we would have two potential states, either survival or death. And so to briefly explain the different parts of each component, we have something called TET-R and LAC-I, and these are repressor proteins. That basically means that when they are expressed, they will inhibit the expression of another gene. While for mCherry, that is a fluorescence gene, where basically if it's expressed, it will emit a red light that can be detected. And IPTG and ATC are induction molecules, which means the presence of them in our system, where we can add them or remove them, can lead to a change in state. So going back to my explanation of how TET-R and LAC-I are repressor proteins, what they do is that they actually repress each other. And as a result, that kind of prevents us from having both of these states to occur at the same time. So if TET-R is being expressed, it will repress LAC-I, and as a result, the toxin can't be expressed, and only mCherry, or fluorescent proteins, expressed. On the other hand, if LAC-I is expressed, it will inhibit TET-R as well. However, if we add IPTG to the system, what happens is that TET-R will continue to inhibit LAC-I, but LAC-I will be unable to actually repress our TET-R. And as a result, only mCherry, or red signal, will be expressed. On the other hand, if we have ATC added to our system, TET-R can no longer repress LAC-I, and only LAC-I will be able to repress TET-R. As a result, only our toxin will be able to be expressed, and as a result, that E. coli that belongs to this group will self-destruct. By using this simple model, it shows that if we invest more time and money in this sort of research to develop such devices, we could create synthetic microbes that are able to detect bacteria that are already resistant to our antibiotics. And by doing so, we could be saving so many lives. And this also has a variety of different applications outside of just antibiotic resistance, such as targeting cancer cells and senescent cells. Thank you.